Hello students, welcome back to our channel. This is Gallery Asha Binu. This is your Asha teacher coming with the new lecture of our dual nature of radiation and matter. So welcome back to our channel. A very good morning to all of my dear students. Hoping all of you are doing very well with your studies and are also safe in your home. Okay, so in the last lecture, we have discussed our dual nature of radiation, electromagnetic radiation, and today's lecture we will complete the chapter by discussing the dual nature of moving matter. Okay, so let us start. So today's topic is dual nature of moving matter. We know what is a matter. A matter is anything that has some definite mass and occupies some space to rest. So all of us are matter. All of us have certain mass. That is, we shows our particle nature. Matter, including me, you, and everything surrounding us is matter. Okay, so matter has its own particle nature because it has a definite mass. Already we know matter is a particle. But it was de Broglie who first identified the wave nature of matter also. De Broglie told us that a matter shows not only the particle nature but also the wave nature. A matter has a capability of showing both the particle nature that we already know and also the wave nature. Okay, clear. That was the importance of de Broglie's hypothesis. According to de Broglie, a matter, if it is moving, that was one of the conditions, we will discuss that. A moving matter shows both the particle nature and the wave nature. When a matter which is moving, so a moving matter shows the particle nature. According to de Broglie, a matter shows the particle nature. Its energy can be taken as E is equal to mv square. Do you know the equation E is equal to mc square, mass energy relation? Since this is matter, our speed is not a c, we take the speed of the matter as v. So the energy becomes E is equal to mv square, just like mc square. So de Broglie said when a matter act as a particle, its energy is taken as mv square when it shows the particle nature. At the same time, when it shows its wave nature, a matter energy can be taken as E is equal to the same energy can be taken as E is equal to h nu or hv by lambda, since V is equal to nu lambda, like C is equal to nu lambda for light and this for our matter. Okay. Now, this equation when the matter act as a wave. So, according to de Broglie, when a moving matter act as energy, when a moving matter act as a particle, its energy is taken as E is equal to mv square. And when the same moving matter act as a wave, its energy is taken as h nu or hv by lambda. That means the energy is same. Either it act as particle or act as wave, its energy is same. Therefore, we can say the energy of the matter when it act as a particle is equal to the energy of the same matter when it act as a wave. Therefore, mv square is equal to hv by lambda. V cancelling, we can write mv is equal to h by lambda, or finally lambda on cross multiplying, lambda on LHS and V on the RHS. We get the equation lambda is equal to h by mv, and this equation was called as de Broglie's matter wave equation. This equation is called as de Broglie's matter wave equation. That is the equation which shows the matter as a wave. The equation which shows the matter as a wave. Okay, so de Broglie's equation states that the wavelength of a moving matter is given by the equation lambda is equal to h by mv. Very simple. So according to de Broglie's hypothesis, a moving matter acts as both particle and wave. When it acts as particle, its energy is taken as E is equal to mv square, and when it acts as a wave, its energy is taken as hv by lambda. On comparing, because since the particle is same, That is, matter is same, either it acts as particle or wave, its energy are same, mv square is equal to hv by lambda, mv is equal to h by lambda, or we can say lambda, the wavelength of the moving matter, lambda is equal to h by mv, and this equation is called as de-Broglie's equation for matter wave. Very important. Hence, the de-Broglie suggested that any matter, if it is moving, act as a wave, and its wavelength is given by the equation lambda is equal to h by mv. Okay, and what is the speciality of this equation? The speciality, the features of this equation, first one, if the particle is at rest, if the particle is at rest, okay, if the particle is at rest, v is 0. If v is 0, lambda becomes 1 by 0, which is equal to infinity. That is, such a wave, the particle is at rest, then we cannot see such a wave. That wave cannot be visualized. Such a wave, if the particle is at rest, the wave formed cannot be visualized. It cannot exist. So, the wave cannot be visualized. If cannot be visualized, we cannot see such a way, we cannot identify such a way if the particle is at rest. If the particle is at rest. Clear? Is at rest. The second one is the particle is moving. Greater the speed, lesser will be the wavelength, or lesser the speed, greater will be the wavelength. So, for a particle with a lesser speed, slow moving particle will have larger wavelength. That is, the second statement states that, the second thing states that for slow moving particle, slow moving particle, that is, if speed v is less, wavelength will be large. Wavelength will be considerable. Okay. And the third point is lesser the mass. If the mass of the particle that is moving is less, then the wavelength will be large. That is, we can say, for a slow moving particle with very less mass, we can write, for a slow moving particle, slowly moving particle, we can say, slowly moving particle with very less mass, the wavelength will be effectively considerable. Effectively considerable. That was the importance. That is, according to de-Broglie, if the matter is moving with a very slow speed and if the mass of this particle is very less, the wavelength accommodate or the wavelength accompanied with that moving matter will be considerable, effectively considerable. So you have to take a matter with a very less mass and which can move with a very slow speed. Then we can say the wavelength is considerable. Okay, so such particles will show considerable wavelength and effectively the wave nature of particle. So that was the specialty of de-Broglie's hypothesis. De-Broglie said that if the mass of the particle is less and it is moving with a very less speed, the wavelength of the particle will be considerable, and such a particle shows, such a matter shows wave nature more than its particle nature. Okay, that was the concept introduced by de-Broglie. So according to de-Broglie, a moving matter shows both the particle nature and wave nature. If it acts as particle, its energy is given as E is equal to mv square. And when it acts as the wave, the same energy is taken as h nu or hv by lambda, where nu is the frequency and lambda is the wavelength. We can say the same matter act as particle and wave, so their energies are also same. mv square is equal to hv by lambda, mv is equal to h by lambda. On cross multiplying, we will get lambda is equal to h by mv. And this equation was called as the matter wave equation, introduced by de Broglie. Okay, and from this equation, it is understood that if the particle is at rest, V becomes 0, lambda becomes 1 by 0, becomes infinity. That means such a wave cannot be visualized. We never visualize such a wave. We cannot say anything about such a wave. Okay, that means if the particle is at rest, no such waves are created. That is the thing. The second, if the speed is larger, the speed of the moving matter is larger, wavelength becomes small. Therefore, we can say if the speed of the moving matter is less, the wavelength becomes large, the wave nature becomes effective or considerable. And suppose the mass of the moving particle, slowly moving particle, okay, is very less, the wavelength becomes effectively considerable. That is, for a slowly moving particle with a very less mass, the wavelength or the wave nature of the matter will be prominent. Okay, this was the concept introduced by de Broglie. Clear? Okay, so de Broglie's matter wave equation is lambda is equal to h by mv. Hoping you have taken the notes. Okay, sorry, I have run the board. So, lambda is equal to h by mv. Once more taking the equation, lambda is equal to h by mv. This is our basic equation. And in the smaller classes, we have studied mv is the momentum. So, the equation may also be taken as h by mv. H by momentum is p. And if you take the relation of momentum and energy, you will write momentum p is equal to root of here. Okay, 2me. Do you know this equation? Yes, kinetic energy and momentum are related by the equation. Kinetic energy is equal to p square by 2m, or momentum is equal to root of 2m kinetic energy. This energy is kinetic. You will write the same equation as h by root 2me. Okay, clear? And sometimes the energy of the moving electron is taken as very small particle. If I take a very small particle, charged particle or subatomic particle like electron, the energy is given as electron volt. So this equation may also be written as h by root of 2m eV, energy in the form of electron volt. So we can take the de Broglie's equation in various forms. What are the various forms? The basic equation is h by mv. Mass into velocity is momentum, so we can take it as h by p. Momentum is root of 2m into kinetic energy, so we can take the equation for lambda as h by root 2me. And also the energy as electron volt, then it becomes lambda is equal to h by root 2mev. Clear? Okay, so the various forms of de Broglie's matter wave equation are lambda is equal to very important, lambda is equal to h by mv, h by p, h by root 2me, and also h by root 2mev. That is, if the wavelength of the matter is asked by giving the velocity, you have to take the first equation. If momentum is provided, then take lambda is equal to h by p. If energy, kinetic energy is provided, take the equation lambda is equal to h by root 2me. And if the potential difference is provided, then lambda is equal to h by root of 2mev. All of the equations will give the wavelength of the moving matter. Okay, clear? So this was the hypothesis given by de Broglie, considering any moving matter as a wave. Clear? Okay. And finally, de Broglie suggested the wavelength of a moving electron. If you take a moving electron whose mass is known to us, whose charge is known to us, Planck's constant is already known to us, 6.6 into 10 raised to minus 34 joules per joule second. Mass of electron 9.1 into 10 raised to minus 31, and charge of electron 1.6 into 10 raised to minus 19. So he provided the values of mass and charge of an electron to this equation. De Broglie considered a moving electron. He considered a moving electron For an electron, the mass is 9.1 into 10 raised to minus 31 kilogram. The charge is 1.6 into 10 raised to minus 19 coulomb. And Planck's constant 6.6 into 10 raised to minus 34 joules second. Everything we know. Okay. And by considering the values, he had taken the wavelength of moving electron as h by, he put the values 2me into v, providing the values, the wavelength of electron was given as or obtained to him as 12.27 angstrom by root of v. That is, de Broglie even provided the wavelength of moving electron. The wavelength of moving electron is taken as 12.27 angstrom by root v, where v is the potential difference. If you provide a potential difference of 1 volt, root 1 itself, the wavelength of electron becomes 12.27 angstrom. If you provide the electron a potential difference of 100 volt, then root 100 means 10. 12.27 by 10 means 1.227 angstrom. That means he even calculated the wavelength of the moving electron. Clear? Okay, so this was the concept introduced by de Broglie, assuming that any moving matter can act as wave also. If the matter has very less mass and it is moving with very slow speed, then its wave nature is prominent. Its wave nature is very much prominent. Okay, and he even give the wavelength of a moving electron. If the electron is provided a potential difference of V volt, the wavelength of such electron will be 12.27 angstrom by root V. Clear? So this was the concept introduced by de Broglie about the matter wave, matter as a wave. Take the notes. Clear? Okay, so now we understood the concept of de Broglie's matter wave. Yes, de Broglie tells us any moving matter act as a wave. But the de Broglie's matter wave concept was experimentally proved by two scientists named Davison and Germer. The concept of de Broglie's matter wave was experimentally proved by Davison and two scientists named Davison and Jama. They conducted an experiment, and for this experiment and for this proof, they were rewarded with a Nobel Prize. Okay, such a great experiment was that. A very simple setup. In order to prove de Broglie's concept, Davison and Germer had taken a experimental setup, which consisting of an electron gun. This is an electron gun. What is this? A gun which releases electron from it. Electron gun. Okay. The electron gun was connected to a very low tension battery. Low tension battery. The electron gun was connected to a low tension battery. When it is switched on, what happens? The gun consisting of a tungsten filament. It consisting of a tungsten filament. The gun has a tungsten filament. When it is connected to low tension battery, what happens? The tungsten filament releases electron, and it has a barium oxide coating also. Tungsten filament having barium oxide coating. So there is an electron gun. What are the features of the electron gun? The electron gun consisting of a tungsten filament which having a barium oxide coating, which is connected to a low tension battery, and when this is switched on, what happens? Electrons are released from this. Now, these electrons coming through the gun are then passed through a cylinder which is provided with a high tension battery. This is a high tension battery which provides a very high potential difference, so that the electron, when passes through this cylinder, attains electron got potential difference. That means that their kinetic energy increases, their speed increases. Okay. The required speed is provided by this high tension battery. The required speed for the electrons was provided by this high tension battery. And when this high tension battery connected cylinder is taken and electrons are allowed to pass through this cylinder, what happens? The speed increases to required value. At the same time, the electron beams become collimated. That is, the electrons begins to flow in a straight line. Collimated beam means straight line electron beam is obtained. So the electron beam, straight line electron beam travels through the cylinder, and finally this is a nickel target, nickel crystal, which act as a target. The accelerated electron falls on this nickel target and gets scattered by an angle, so that these electron comes through here, and here there was a movable collector which collects the electrons and detects the angle of scattering. Movable collector. Okay, clear? And the whole arrangement was kept inside a vacuum chamber. The whole arrangement was kept inside a vacuum chamber. Clear? So this was the experimental setup taken by Davison and Germer. Very important experiment. That is, at first they had taken an electron gun. Okay. This electron gun consisting of a tungsten filament with a barium oxide coating. It is connected to a low tension battery. When it is switched on, this electron gun releases electron which passes through a cylinder having certain pores. The cylinder is provided with a or connected to a high tension battery which provides the suitable potential difference. So the electrons which passes through the pores of the cylinder, the holes inside the cylinder, becomes collimated. That is, their path becomes straight line. At the same time, the potential difference provided will provide the kinetic energy and the speed becomes required. They attain collimated electrons with the required speed. These accelerated electrons were then made to fall on a nickel crystal, which act as the target. And these electrons are scattered by an angle phi. And these scattered electrons are collected by a movable collector, and the whole arrangement was taken inside a vacuum chamber. Okay, so this was the arrangement, the experimental setup of the Davison-Germer experiment. Clear? And what they have done, Davison and Germer provided various potential difference. That is, they provided potential difference ranging from 44 volt to somewhat 68 volt. They provided the potential difference ranging from 44 volt to 68 volt by this high tension battery. Okay, as a result of which the electrons, the scattered electrons were identified by providing various potential difference. They analyzed the scattering of electrons, and finally by plotting a graph of intensity of the scattered, this is intensity. Then when they plot a graph of intensity of scattered electrons with the potential difference provided, they got a graph like this. The graph obtained was like this. The intensity was maximum. The intensity was maximum for a potential of 54 volt. The intensity was maximum for a potential of 54 volt. That is, maximum intensity is obtained at 54 volt. Finally, they identified the intensity is maximum at 54 volt, where the angle of scattering is obtained as 50 degree. The angle of scattering was taken as or obtained as 50 degree when the voltage was 54 volt, where the intensity of the scattered electrons was maximum. So finally, from this experiment, plotting the graph of intensity of scattered electrons with the potential difference provided, Davison and Germer finally proved that for a 54 volt, the scattering angle was maximum. The scattering angle was maximum, which is equal to 50 degree. Clear? That was the experimental observation Davison and Germer get from this. And finally, this 54 volt was provided to de-Broglie's equation. Lambda of electron was given by de-Broglie as 12.27 angstrom by root V. When they provided the value of potential difference as 54 volt, okay, they got the value as 1.65 angstrom. The wavelength of electron was obtained as 1.65 angstrom by providing the potential difference, this potential difference to de-Broglie's equation. Okay. Okay. So this was the wavelength of electron as per de-Broglie's equation. And what they did, the angle of scattering is 50 degree. Angle of scattering means if this is the atomic plane, if this is the atomic plane of nickel atom, atomic plane of nickel crystal. Okay, nickel crystal, what happens? This is the next color. Yes, this is the angle of incidence theta, and this is also angle of incidence theta. What is theta? Angle of incidence. What is theta? It is angle of incidence. Theta, this is phi, this is theta. That is, from that we can write 2 theta plus phi becomes 180 degree, or phi becomes, phi is our, yes, you got 2 theta plus 50 is equal to 180 degree, and 2 theta becomes 180 minus 50, 130. Theta becomes 65 degree. Okay, from this they got theta as 65 degree. Clear? I have to just check my, no problem, everything is in. So 2 theta becomes the 130 degree, or theta is equal to 65 degree. That is, when the angle of incidence is 65 degree, here the angle of incidence is 65 degree, and providing this value of 65 degree angle of incidence for a particular equation called as the Bragg's equation. Bragg's equation for diffraction. Bragg's equation is not in this topic, that is discussed in the solid state of your chemistry. There, in order to study the crystal structure, there is an equation n lambda is equal to 2d sine theta, where theta is the angle, this angle 65 degree, d is the distance between the nickel crystal, atoms in the nickel crystal, d is equal to somewhat 0.91 angstrom, that is already calculated value, n first order, on substituting the value of n, d and theta. On substituting the value, n is equal to 1, n is equal to 1, d already known 0.91 angstrom for nickel crystal, the distance between two atoms in the nickel crystal, and theta is 65 degree. The wavelength on taking this got as 1.67 angstrom. That is the angle corresponding to this 54 degree, the angle of incidence corresponding to the 54 volt. On providing that angle to our Bragg's equation, which is purely for diffraction, Bragg's equation, which is purely for diffraction, the wavelength obtained, the wavelength of electron obtained is also same as that of de-Broglie's hypothesis. Okay, so what they did at first, considering the 54 volt where the intensity of scattered electron is maximum, they got the angle of scattering as 50 degree. Taking this 50 degree and taking the angle of incidence, they get 65 degree. Providing the angle of incidence 65 degree to Bragg's equation, it satisfies the Bragg equation, and providing the 54 volt to de-Broglie's equation, it also satisfies the de-Broglie's equation. What does it mean? This means that the electrons are not scattered but are diffracted by the nickel crystal. Since the electrons now obeys the Bragg's equation for diffraction, a phenomena which is purely shown by the wave nature. Electrons' wave nature is proved by this condition, that is, by taking or by considering Bragg's equation, where it satisfies the Bragg's equation. Electron now satisfies the Bragg's equation, means that the electron now acts as a wave. It satisfies the condition of Bragg's equation. That means it acts as a wave. A particle never shows diffraction. Only a wave can show diffraction. That means electrons are scattered, not scattered, but are diffracted by the nickel crystal. That was the conclusion of Davison-Germer experiment. Take the notes. So from Davison-Germer experiment, it is proved that electrons are not scattered but are diffracted. Since they satisfy the Bragg's equation, this equation important for solid structure crystal study, where the diffraction is employed. These electrons are diffracted by the nickel crystal, and since the diffraction is a phenomena shown only by the wave nature, electron shows their wave nature, which which proves the de-Broglie's concept of matter wave. Thus, Davison and Germer's experiment proved the wave nature of, or the de-Broglie's hypothesis of wave nature of moving matter. And they were awarded with Nobel Prize for this experiment. So this was the topic which we have to discuss in this chapter: dual nature of radiation by photoelectric effect and dual nature of matter by considering de-Broglie's concept. So we have completed the topic. Hoping you understood it very well. And till the next class, see you. This is our channel, Physics Gallery. Ashabinu, hoping you understood. Any doubt related to the topic, please, you may ask. See you.